Okay, so today we are very grateful to have Dr. Theo Drane, who leads the numerical hardware and system level design group at Intel, who's working on all aspects of architecting, implementing, optimizing, and formally verifying mathematical intensive hardware and system level design. And today he's going to tell us new directions in numerical hardware design methodology. Theo.
Okay, thank you very much, Wayne. I'm based in the Intel graphics group within the microarchitecture team. And essentially, we get to optimize all the different complex and varied algorithms that you have in graphics. Now, my interest is in numerical hardware design in general. And what that actually makes graphics very interesting is the sheer diverse range of algorithms. And also the constraints on them are sometimes quite non-obvious. So here's one of my favorites. And this is one of the many reasons I'm in graphics as an application. So buried in GPUs is this question of you have to make texture appear on the screen somehow. And this is one of the the least obvious algorithms that you need fixed function for. And the great thing about this is it also ultimately just has to look good. So the wonderful thing about this challenge of making fixed function hardware for this is the definition of correct is not obvious. And even the algorithm you would implement in hardware is not obvious. And there's just layers upon layers of approximation going on when this hardware is designed. So the approximation that's used when you map, I mean, ideally, of course, you would be mapping a texture onto some 3D geometry and then onto the screen. Obviously, you wouldn't waste your time doing that. So we're actually mapping directly from the texture onto the screen. And that's it done, if it's done perfectly, would be a very non-obvious transformation. Now that's approximated by an affine transform. And what that would mean is a circle in screen space becomes an ellipse in text space. And I've just done this very cut down toy example of what this would look like. Imagine if that transformation was buried in this 2D matrix, that in this case happens to be symmetric. One of the things you have to do is work out how big is the ellipse that you end up with in texture space. So the exact details aren't fascinating. The only thing that's really interesting at this point is these are non-obvious algorithms. How could you actually go about what algorithm would you use to do this? You have to compute properties of the major and minor axis. You can do your basic linear algebra and you can come up with these interesting equations. There's a whole range of ways of doing this. I won't even discuss numerical stability, but you end up with these interesting computations. And if you were to start to bury this, to actually design fixed function hardware for this, you need a range of components. And what's interesting about this is really what you have off the shelf. So one of the many wonderful things of GPU design is we actually have over 250 different number formats. If we even take this design, we expect the inputs are floating point, the output is actually fixed point. The internal formats are entirely up to us. And what this leads to is this question of, well, we need to build these components. But we actually have countless choices buried in here as well. Are we making, obviously we need floating point adders, we might need dot products, do we actually build division, do we just do reciprocal? You have all of these different questions. And what's really interesting about these kind of design challenges is that they violate the most basic way in which hardware is typically designed. So one typically imagines this very simple structure where somebody writes some system level model, which is then from which HDL is created, and then we might optimize it. But this very toy example I'm showing, makes it very clear very quickly that that isn't going to work. So I need these components, but that's probably more than a question of, well, do I have existing components if I want to just get this done at speed? And then what C models do I have lying around? I mean, obviously, the way this functions is we are designing HDL. We typically have an independent C model. You know, you simulate between these two for correctness, but really it's about what do you have lying around, and do you need correct rounding or not? You know, so this is a completely fixed function thing. As I've shown you earlier, this is an approximation. If I then start introducing errors into these atomic operations, they're just layers of approximations. So there's this question of what should the design actually be, and how accurate do these components have to be? And then you very quickly run into needing bespoke hardware. So this is going to be quick. And even worse, the thing that's particularly entertaining is some of these things that we're doing here violate the toy way in which work is done. And by that I mean, if you have an atomic function that is correct to a unit in the last place, basically you're not implementing the IEEE standard. So actually it's in the design of the hardware that you would actually work out what the bit accurate correctness of your hardware is going to be. So implicitly, we actually end up deriving the system model from the HDL. So this is from a methodology perspective, this violates all of the nice properties that people think of how hardware design is done. And then the other problem is, for these fixed functions, we don't have to use standard precisions for floating point throughout. And if we're stuck with the normal precisions, we would end up just choosing, say, between half precision and single precision. But really, it really depends on what the components we have lying around is. So in reality, what happens for these kind of fixed functions is we end up with some very unreadable, sometimes bespoke C models, and some of it's actually hand-derived from the HDL itself. If we were to do a specification, we might be forced, just because of components we have at our disposal, to use, say, single precision, so FP32 throughout. And then what's very strange is if we had the HDL and we had the C, typically one simulates between these two to gain confidence of correctness. But if the C was derived from the HDL in a certain way, what is the value of this? And, you know, we haven't even touched on how do you prove algorithm correctness. So basically, this is the mess that really happens when you try and build fixed function, particularly for these interesting algorithms. So that's the state of play. And so as we've been working on how to deploy excellent hardware that is correct at speed, what exactly are all the optimizations we're doing? And what actually is the hardware optimization problem that we're trying to solve? So we have an absolutely enormous array of handles that can be turned to build the hardware. So here's kind of the most obvious optimization problem. We are trying to optimize a particular feature of the hardware performance. We need to make sure that it is application level correct, which in this case is actually non-obvious, which makes this interesting. And what are the things we play with? Well, obviously, we have to choose algorithm. There is the architecture, which is how some of our components, which components do we build? How do we use them in a temporal setting? But as I kind of hinted about GPUs, we have hundreds of different number formats. We can use any precision we like. We can use any accuracy we like. And then even once we have something that is bit accurate to our intent, then of course there's countless RTL optimizations you can do. And then even in RTL, you might do some bit level optimizations. And once you get to logic synthesis, then it's going to do even more bit level optimizations. So this is the actual problem. But what is very interesting is for any design methodology, Where is the time spent? Who has the expertise? And it's actually very entertaining. We basically have essentially these two inverted triangles. So it's kind of obvious that the power to alter your final power performance in area, PPA, basically descends actually quite rapidly as you make these choices. So obviously algorithm, it's very interesting. With this trivial ellipse example I showed, if I rewrite my equations even slightly, then I completely alter the bit accuracy of the resultant hardware, and I alter its PPA. But obviously, as you go down this cone, your ability to alter the PPA drastically shrinks. And then the other side of it is, what is the rate of change of the hardware? So typically the algorithm isn't going to change that much, or the original application requirement doesn't change that much. But then the architecture can, and of course the precisions may change, the accuracy of the implementation may change. But one of the saddest elements of this as well, which is there's an enormous amount of focus down at the RTL level, and people haggle over this all the time. And that's where the bulk of change is, but it's potentially already fixed by the time the algorithm is fixed. So you have these opposing forces, and it's really interesting about what design space exploration you could do versus what is done versus what is automatable, and why people are focusing on different aspects of this. And this really boils down to the obvious statement, which is, are people doing what they can do as opposed to what they should do? Are we missing tools and methodologies to actually do this quote unquote properly? So I'm going to now propose a 6-step solution to this. And essentially, we have been working on this, pieces of this, for obviously quite some time. And some of this work is literally fresh off the page. Where we're currently doing a multi-year collaboration with Imperial EE to pick on certain challenges in this way. So let's begin with step 1. And what's really interesting about this is that we're looking at algorithm design. And the weirdness about this, if you think about a standard hardware process, I kind of hinted that if I were to change the accuracy of a low-level component, then I've actually changed the bit accuracy of the entire algorithm. So don't I need to actually have a C model or finished HDL before I can say whether anything's any good? But the underlying problem is, how do you start this design process without having HDL? Because you need, you have all of these different handles to turn. You need to find a way of seeing if your algorithm is any good in any way, shape, or form. And so essentially, I would like to run my algorithm, and I want to focus on the algorithm. And what does this actually mean? Is particularly at the beginning, we were involved in visual technologies. I really need to get a handle on what correct is. And this is typically something that we're not going to get from our C models. So I really do need access to real numbers. And this led us to this. This is an academic project that comes out of the University of Washington in Utah, which is basically, we need a way of capturing algorithms. And this project called FP Core, its purpose originally was they would like to see how different number formats affect software programs. So whether it's, what if I change singles to doubles, what kind of impact do I have? And they built a benchmark environment to help researchers using different tools to see, building different tools to see how their tools would affect different programs. And so they built FP Core as a language to express intent. They wanted something that was the purest mathematical intent with additional features. So, for example, what FP Core allows you to do is write essentially the pure mathematical specification. So here we would take, in this case, this is actually the equations for the minor and major of the ellipse I mentioned earlier, and we can bury that in FP core. And if you were to simulate this, you're essentially under the hood using something like MPFR with potentially hundreds of thousands of bits. But the key value of this language is it allows you to then start introducing finite precision. So as an example, you can add these annotations, which basically says use single precision throughout all of this. But of course, the other key value is multi-precision. And if you actually dig into this, what you can actually see is that you can define, you need this interplay between the real arithmetic answer and the finite precision. So what's interesting about this language is it allows us to say which precision we're using where, and therefore implicitly, what's an atomic operation. And particularly kind of I hinted at the beginning example, we have some weird components we may want to build. We may want to build A times B plus C plus D, whatever it is, but you can capture that in this language. Because at this stage, you can basically say, I want the real answer to a particular atomic function, and only then do I cast it to fixed precision. So essentially, this language allows us to declare intent and clearly also mess around with intent. As you can see, bottom left, we've said make the single precision. Bottom right, we're just annotating places with precision that we don't know yet. But this essentially, this language and its simulation allows us to play with the algorithm itself, even to say, let's call it infinitely precise. So we can write an FP core, we can simulate it. In graphics, this is clearly valuable because we can actually even build visualization on top of this. But essentially, we can get a handle on the algorithm to some notion of infinite precision to see whether it's even correct. And this allows us to link an application with the algorithm without even touching some of the other topics. So that's step one, basically. This is a really vital piece of the puzzle. You need a machine-readable numerical specification. You clearly need access to real numbers. And this is particularly poignant nowadays with machine learning number formats. I mean, you will have obviously seen the zoo of number formats that exist. There's two different definitions of 8-bit, there's 16-bit, there's two different formats for that, there's 32-bit. In graphics, we use at least 40 different floating point precisions. So you need an agile specification language, and it's not C. So that's step one. So this, you can get basic by simulating against infinite precision, AKA MPFR, you can check the basic properties of your algorithm. But you can then do something else with FP Core, which is incredibly valuable, is you can do the smoke test. Now, basically, as I mentioned, we do not want to, we're not ready to say what precision that we intend to use. But we can do something very simple to see whether an algorithm is broken. And so this is one of the things that you can do with FP cores, is I mentioned there's annotation sites. You can say which precision you want. But what we can do here is we can say, let's just take an FP core, let's assign differing precisions, and let's just do a simulation. And we can look at worst case average versus the infinitely precise value coming from MPFR. And we can actually build this Pareto from it. And on the x-axis, we've done something really stupid, but will actually turn out to just be quite invaluable, which is we need some really trivial cost, something linked to the cost of hardware. So as a dummy cost, we're using the sum of all of the internal precisions. So you fix your algorithm, you put your annotations in, and then for any given implementation of different precisions at different places, you just add up all the precisions. Now, this is a stupid metric. It won't correlate to hardware cost. But one thing it does do, it does preserve ordering. So from what that means, if I take a particular set of precision assignments. And if I were to shrink one of those by 1 bit, then of course I expect the resultant hardware to be less expensive to build. So we have an ordering. At this stage, all we care about is the ordering. So we can actually simulate FP cores with lots of different precisions and create this Pareto frontier. But what's incredibly interesting about this Pareto frontier is it can end up being broken. And by that, it could simply be this, that if you form this Pareto frontier, there are cases when it becomes, you basically hit asymptotes. So in this case that we looked into, the number of output bits is 16, and the average number of correct bits can't get above 10. So that kind of tells us that there's not really much point. We're never going to, we shouldn't even be producing 16 bits because the other 6 bits are noise. But something's even far more disturbing is this plateau. And what this plateau is telling you is that even if we were to add hundreds of extra bits, we don't get anything more accurate. And so this is clearly a complete disaster. So basically this is how we detect numerical instability, which basically means your algorithm itself is bad. So this idea that you could add hundreds more bits, but you won't get more accuracy, clearly you're not going to build that hardware. But what it also means is if you did use this algorithm, clearly you'd be burning a lot of hardware to achieve the accuracy you want, compared to an algorithm that is numerically stable. So what's particularly fascinating about this is, yes, we haven't done, there's no formal verification we've done here, but this is a smoke test. And even with basic simulation, you can detect numerical instability of your algorithm. And what's interesting here is we're still talking about the algorithm. We haven't yet chosen the precisions. But using this kind of simulation technique and implicitly trying multiple different precisions, we can just detect if an algorithm is broken. And that means we can go back to the algorithm board. Now, the whole purpose of these steps that I'm explaining, of course, is you need to fast fail. And so these 2 steps, 1 and 2, allow you to fast fail on the algorithm itself before you even touch the murkier details of hardware. So by this stage, you can then change your algorithm, you can investigate numerical instability. And of course, every time you rewrite your algorithm, ultimately you would ultimately have ended up building completely different hardware with very different accuracy behaviors at an application level. So you can use this process to iterate purely using FP core and a simulator of FP core, and one that can produce these curves. And then eventually you should be happy. And eventually you should be happy, which means once you've done your smoke tests, you, as I said, you are already choosing which components you intend to build. We have certainly not done any work on automatically working out the best components to build. It's a different question. And if your algorithm is numerically stable, you'll have something like this. This is a nice Pareto frontier. It doesn't have an asymptote. So basically, you then get to pick. It's in truth actually could be very contentious. You need to know, this is still simulation, by the way, but you can actually select where on the accuracy kind of hardware trade-off. Yes, it's a dummy cost, but still this is a way of trying to choose precisions, a multi-precision that would actually give you, we suspect to give you an accuracy that you would care about. So what every single point on this frontier contains is an assignment to the precisions in your data flow graph, so they can all be different. So this would actually give you a multi-precision implementation. So this is the moment when essentially you've chosen the algorithm through refinement by simulating the FP cores. Here, we are obviously fixing the components implicitly by where we put these precision annotations, and generating these Pareto frontiers and choosing a point off it would allow you to then choose which precisions you're going to use. throughout your algorithm. So those are steps 1, 2, and 3. And so far, this is all an FP core game. And it is interesting to note, we have done some coding and there are some simulations, and we have achieved algorithm understanding with no hardware whatsoever. And this is all essentially what ifs. What if we did build this? So the only way to actually answer that question is to explore multiple designs. And so what's very interesting is this Pareto curve. We're exploring thousands of designs very quickly, essentially doing smoke tests on all these multi-precision designs. And of course, even looking at these Pareto curves, we can see if something is broken before we even spend the energy on building hardware. So at this stage, we now know what a good algorithm looks like. We have essentially chosen the precisions we intend to use at each place in the DFG. So what do we do now? So basically, this is one of the interesting holy grails, because if we kind of stand back and say, what are we trying to achieve? How do we reason about hardware? What kind of tools do we need on top of this? Essentially, what we've just done at an FP core level is we're actually dealing with infinite bit widths, arbitrary precision implementations. Now, once we've made a choice we believe is a good FP core, then we have to descend into the mess of implementation. And now actually there is a massive cliff edge jump. And this is one of the many reasons that there aren't really tools that industry is using for this. Is essentially, yes, you can have your infinite bit widths. You might end up doing pen and paper computation, whatever it may be. The FP core is the space where kind of theorem proving or could actually be applied. This is your pure mathematical intent, even though we've started to add finite precision. But we now need to get stuff done. And so what that means is we need a C model of what we intend to build. And that has to have reasonable bit widths. Some of these models won't even load into tools if you have these kind of very, very large bit width models. So we want reasonable bit widths so we can start to produce, a C model. This can be used in compliance tests, things of this type. This can be used by the rest of the division. We then need to know, we need an estimate of the HDL cost. So we need something that is then reasonable performance. And then ultimately we need to refine it so it has best performance. So this is ideally what we would like. And typically, of course, this is done by hand, and there may be no way of linking these models together or proving that these models are equal, or even ideally deriving these models from each other. So let's have a look about the first one. The first step is the most horrific and the most important. So I'm going to choose as a vehicle for this something incredibly simple, but I think it will illustrate the point. Buried in our algorithm, we have these components. Floating point addition is clearly very common. We obviously have hundreds of these in a GPU. So what is floating point addition? Now, from an FP core perspective, if we were to write the most vanilla model for what floating point addition is, you would have this vision of, these are just ultimately fixed point numbers aligned in some way. And if you wrote the most stupid model you could think of, it would have internal bit widths, hundreds of thousands of bits in length, but it would be incredibly trivial to inspect and check. It would be the simplest mathematical intent you get away with. But these models are absolutely no use to the industrial division. You can't even load these into any of our industry tools. However, you could do algorithm level reasoning. It is possible to do it at this stage. So how do you actually descend the mountain? Well, obviously, in truth, and this looks trivial, but of course it's far from trivial. So floating point addition, obviously at a hardware level, there's countless tricks how you build it. But even if you were to make a C model, what is the most vanilla C model is not obvious. because what actually goes on in your even vanilla C model is you have optimized it somehow. So what goes on in the vanilla C model, obviously, is if I were to add and subtract these two fixed point numbers on the left, if I want to know where the significance is, well, you know that something, say, down here, which has lots of barely any significance, this is ignorable. And so you don't need hundreds of bits, you just need tens of bits. Now that's done. That reasoning is actually non-obvious, and you have to have a formal proof that you haven't broken it, which then means you're comparing against some other model that probably itself only has tens of bits. So there's an immediate trust question. And there's some lovely corner cases in floating point. So even if you wrote the most simple C model that uses tens of bits, it's still highly obfuscated. It can, of course, be loaded into industry tools. But essentially, once you've done this jump, if you don't have any hope of doing algorithm level reasoning, you wouldn't use this model to do this. You would have to assume the model on the left or something cleaner. Now, the interesting thing is, can we jump from the left to the right? And actually, some of our latest collaboration with Imperial EE, and I will hint at some of that, what form that work takes coming up, has the power to do this. What is interesting about this kind of rewrite, this is clearly a rewrite engine, but it has to really, there's value range analysis in here. What's very dangerous about this tool, and also wonderful, is if you had a tool that could rewrite the left to the right, then you don't actually have an industry tool to prove its correctness, because the left-hand side doesn't load into an industry tool. But essentially, having an automated jump between these is the descending of the mountain, because the right-hand side, finally, we have something that we can use in tools and reason about with standard industry tools. But the left is the intent. And this gets particularly vital when people are haggling over intent. As you can imagine with some of the new machine learning algorithms, we're looking at FP8, 8-bit float format, but it's mixed precision. You'll then use FP32, you're converting between these. There's lots of nasty corner cases that you need to reason about. So anyway, so this is some of the latest work we've done to essentially bridge this gap. And what it means is we can achieve this. So we're building up a tool chain that takes in FP core and spits out C models. And by design, very carefully, and this is essentially say new work to some degree, is these models have to be simulation and formal friendly. Not all industrial modeling languages used from GPU simulator are formal friendly. So we're picking through the generation of this, and this tool, obviously, in its first instance, is substitution based. We're not doing the automatic rewrite I mentioned, but we do know how that rewrite could go. So essentially, once you've done all your precision analysis, you've chosen your precisions, you have an FP core that you like, then this tool chain will convert it to a simulation and formal friendly C model. And what form could this take? Well, obviously, if the FP core says A times B, even if it is with floating point precisions, then we can just substitute for a known C model. If we have known atomics, obviously we can substitute them. If you have unknown atomics, because if you remember back to the start of the talk, I had some interesting components, like I would like to build A squared plus 4B squared or something. So we need to be able to build atomics that we haven't seen before. So the obvious thing to do in the short term would be use a lookup table, but obviously that's limited. But the longer term, hinting on what I just said earlier about the rewrites, is in theory, could we do this automatically by taking a quote unquote infinitely precise model and then rewriting it to something with reasonable bit widths automatically? So we think we know how that could play out. But essentially at this stage, the most obvious one is I can do substitution with known optimized C models. There was a correctness question. That's a whole different ballgame. But essentially the correctness problem has now shifted. In the past, people would have written these C models by hand, particularly for any weird bespoke combination of precisions. Here, this is now a compiler design problem, which obviously has just moved the problem. It hasn't deleted the problem. But then the problem becomes about validating the compiler, which at least has, should we say, some generally more deterministic behaviors than the human C model creation. Okay, so now we've crossed, now the mountain descending is done, we can now do something with this. So from an FP core, we have our C model. This is going to be a bit accurate C model. So we can, for the first time, throw that into application level testing, compliance testing, you know, for graphics, you've got all these different compliance suites that you can run to see whether this would work or not. And then the other qualification, of course, we want to do is, can we get a measure of hardware? And so the quick and dirtiest way of doing this is another substitution. Can we create some system C for these atomics that are in the FP core? It would be a substitution-based thing, but it would give you power performance and area estimates for the first time if you threw it into high-level synthesis or something of this type. So that's essentially the qualification step. Once we've descended the mountain and got a bit accurate model, we can then start to get application level testing and estimates out the door. And I'll give you also a hint about how, you know, I mentioned we could do it with substitution, but how could you actually automate this? And this goes back to some of the latest Intel Imperial work. Essentially, that floating point adder example, you need to reason about value ranges. And so some of our latest collaborative work uses e-graphs. So first of all, what these are is, this expresses multiple different data flow graphs at the same time in a compact way. This allows you to explore multiple implementations. Each of these has very different PPAs. So we're using that technology. Obviously, to solve that floating point adder conundrum, you have to know something about value ranges. And so the collaboration really hinges around taking e-graphs, applying interval arithmetic, and using techniques from abstract interpretation to achieve these kind of fundamental transformations to code. And this would allow us, in theory, to not only build the C model automatically from an infinitely precise FP core, this could give you this could give you PPA estimates that are realistic. Because, for example, for floating point addition, you're not going to synthesize the 1000-bit thing that we had at the top of the mountain. You need some, ideally, automatic technique to make the bit width reasonable, which is what this technique offers. And then finally, highly optimized HDL creation. Part of that collaboration, the Intel Imperial collaboration, is around this tool called Rover, which its ultimate goal is to take behavioral HDL and do large design space exploration and produce optimized HDL. So this is kind of step 6. Now, typically this is a manual thing. We may just take the PPA estimates, take all of the analysis that we've done, and then make the HDL by hand or refine the estimate HDL by hand. But here's one of the steps that it would take. So I've walked through this is what we're envisaging for the 6 steps of analysis. Okay, so let's conclude. So the conclusion is, what is the current / past way of doing this? Just to recap. So for my interesting toying model that I had at the beginning, the algorithm is not obvious. The components you use are not obvious. The precisions, the accuracies, it's all not obvious. But in a standard hardware design methodology, you would basically be forced to make the HDL, and then you would have to scramble and even derive some of the C++ from the HDL. Your specification would be non-executable. It might even just be the mathematical algorithm without any precision annotations. The problem with all of this, of course, is note that the HDL precedes the C++, which means that whatever design process went through in this case, you have to go all the way through to HDL to then generate C++, and only then can you start seeing if you'll pass compliance. So basically, there is really no intermediate steps. There is no feedback loop until you have the HDL. So there's any of the nice properties, there's no fast fail here. This is the longest, most painful process you could possibly get to. So that's normal. And so to recap what those 6 steps were that I proposed, step 1 is algorithm design. So here you would write a machine readable specification, not a lovely Word document. You write your FB core, you can do simulation on it against the reals to see whether you've made obvious stupid errors. So you can do refinement of your FB core. So there is a feedback loop, even at the algorithm level. The next step is to try the multi-precision. Look at those Pareto frontiers. You might discover your algorithm is numerically broken, is numerically unstable. So then you do another feedback loop to the FB core. And then when you're finally happy with your Pareto curves, you can then choose which precisions you want. And by this stage, we have implicitly got feedback from an algorithm, architecture, components, number formats, and precision perspective. Once we've done that game, we can then use this IFP thing. From there, we get our C model, we can do application level testing, we might fail it. So then we have to go all the way back to the FB core. But it's interesting here, we already have 3 points at which feedback has been delivered back to the algorithm. 3 places. And then once that refinement, there may be another larger loop. We can then get some estimates. We can then do some HLS. We can get some PPA estimates. And that in turn could go, this is just nonsense. And that could include things like accuracy of a component. You can imagine an IEEE compliant component could be way too expensive to build. So you have to use a lower accuracy one. So you have to build that into the modeling framework potentially. And then when you're finally happy, you can then polish the HDL. That's where the really important RTL optimizations and bit level optimizations can happen. And ideally, it should be this tool that we're working on that does data path high level synthesis called Rover. So that's essentially the kind of end-to-end 6 steps. Crucially, this allows fast failure. This is one of the vital pieces of this, because clearly you can imagine in a traditional design methodology, the person who designs the algorithm, when are they held accountable to the quality of the algorithm? And it will just take months potentially. This is more about fast fail, early feedback loops, multiple feedback loops of increasing length. So there's a short FP core refinement process, and then you start these larger loops potentially. Okay, so I presented this interesting tool chain. Where does all these tools come from? What's missing? What are we building and what exists? So FP core is an academic reference, specification language. The simulator to an FP core and the multi-precision at the moment is a mix. It has academic open source elements, but it also has Intel elements. The IFP thing is purely in-house. The HLS is off the shelf, and the Rover thing is currently in-house. And then in terms of the roles, which is rather interesting, and this is clearly shall we say, rather ambitious, to put it that way. Like, who's supposed to use these models? Well, obviously, from a C model perspective, once the bit accurate C model is generated, then there's no change to any processes regarding, say, application level testing. From an RTL design perspective, what's very interesting is we expect HLS to give you PPA estimates. That's not a surprise. Rover should ideally give you highly optimized HTL. It may end up being human assisted. But the architecture space is completely different. Typically, architecting for these kind of designs is a paper exercise, where suddenly we have these languages and these simulators. And so in theory, this is the architect role. These are the tools that we would give to architecture, ideally. Now, at the moment within our group, we're essentially running all of these steps ourselves. But essentially, that's where eventually the split resides. And if I pull back from the presentation entirely, we obviously know that from an architecting perspective, you need some kind of machine readable specification, you need some qualification of the algorithm and the architecture before you then force it upon the rest of the execution division. Obviously, from an RTL design perspective, there's been, obviously well more than a decade of HLS promise. Graphics is one of the areas that it really does struggle with. And actually our Rover project is designed to try and fill some of those gaps. But essentially RTL design, is clearly expected for high performance. It's currently all manual. That clearly isn't where the future lies. But obviously from a sheer quality PPA perspective, it is worth the manual effort. But this landscape I'm basically showing is how can tools and methodologies help assist in this process. So I think with this kind of conclusion slide of the overall vision of what we're working towards and have pieces of the puzzle, I think I will close there.
Right, thank you very much, Theo, for a very interesting talk. Maybe I'll ask the first question. In your talk, you hinted that there could be possibility for formal verification. So where would that be?
Oh, great question. So let's pick through this landscape. So let's do the easy stuff first. As I mentioned, this descending of the mountain business. So the mountain descent obviously is this magical line, if I can get my cursor to work. So this vertical line down here is when we cross over into bit accurate things consumable by formal verification tools. So on the right hand side, this is actually quite straightforward. Actually, I completely lied, it's not at all straightforward, but let me go through those. So high-level synthesis. High-level synthesis has, in the industrial high-level synthesis, has no formal verification backing whatsoever. But amazingly, that has changed. So as of the end of last year, there are now, Cadence has released, has a tool that essentially, I think it's called kind of Jasper HEC, which stands for HLS equivalence checking. So your HLS tools are starting to have a formal verification story on them, from the system C, C++ to the RTL. The Rover thing that we're building literally has a, we've built formal verification into it, and I can give you a hint about why that's happily doable. So what Rover does is use this eGraph technology, which is doing rewrites. So actually, let me just dive in. I probably have a useful picture of what this looks like. Do I have this at high speed? Yes, 1 second. Okay, let's do this. Okay, let's do this. Let's swap this over. Okay, so one of the nice things about what Rover is doing, it's using this eGraph technology. So it's doing rewriting. But the really nice thing about this is we own the rewrite rules. So when we actually pull out a particular design, we actually know the full history of which rewrites were applicable. So that actually means we don't just produce an optimized design. We also have the original. We have every single intermediate step. So this allows us to produce a full micro-grained waterfall of what Rover is doing. So that has a full formal verification story attached to it. So let's now go back to the harder stuff. Let's do this. So this allows us some progress into. So there's the start of formal verification for this. We have a formal verification story for this. If it is done manually, then formal equivalence checking between optimized HDL and your estimate, your behavioral HDL, whatever it is, that's a manual exercise, but that's quite routine in the industry. So that's this piece of the puzzle. The problem then, of course, is what is this story? And let's actually zoom in on the IFP tool. So we're building this amazing IFP tool that takes FP core, which is basically the real arithmetic, down to bit accurate C models. How are we going to qualify the correctness of that? So we'll be qualifying the correctness of IFP in the consistency of its outputs. Obviously, we can formally verify what we believe is a supposedly an IEEE compliant floating point at a C model with existing references. So we can test its outputs. But if we then look at the FP core itself, one of the things that we have started discussions over is if the FP core is meant to be the pure mathematical intent, is there something appropriate for theorem proving? And we've started that question. And ideally, you would have an FP core front end to something like ACL2. And because something like ACL2 can also read in RTL as well, in theory, we can start connecting some of these dots. And it would have to be through a theorem proving process. But even if we park that to one side, essentially we can do consistency equivalence checking between everything on the right-hand side of what IFP is generating. To be fair, also, I mentioned about this simulator, this is just simulation based. So it's used, it doesn't make any formal claims that this will give you the accuracy you need. And actually, from an algorithm perspective, we don't really have a robust methodology to prove application level correctness. If we did, what would we actually do in practice? And the first thing you would do, of course, is you would take the algorithm from FP core, which should be the simplest intent, and you might, I don't know, do the pen and paper proofs of that. You can then prove the atomic properties. Whoops, that doesn't work. You can then prove that the atomics are correct. But essentially, at least the FP core embodies, this is the simplest intent model, and that can aid in reasoning in various forms. So there are elements of that puzzle, but it's clearly non-trivial. Obviously, some of these new tools we're building, formal verification has to be at the front and the center of their construction, but it's clearly a non-trivial narrative.
Right. So what's the current state of this 6-step method? That is it sort of, you already use it to create some commercial hardware that we could buy, or it is relatively sort of still at the research stage?
So let's see what I can tell you. Okay, so I will confess, Rover is yet to affect Intel graphics production, but the tool can do, we're just getting to that point now of doing the abstract interpretation into arithmetic reasoning. And this has now the capacity to automatically optimize floating point addition into something that would be competitive compared to some of the obvious known implementations of FP add. So this is going to produce competitive production level RTL this year. That's that piece of the puzzle. HLS being formally verified, that collaboration we have starts this month. So we're collaborating with Cadence on this. The IFP tool chain for the most simple things like, we want mixed precision, floating point addition, multiplication, different bit widths. This is currently, C models derived from this are now, they're in production code. They're not yet in Intel products, but this is in production. The reasoning, discounting algorithms, we have indeed discounted algorithms using this Pareto frontier. So there are algorithms that will never reach production because we've killed them off early enough. So that's the anti-story, that these techniques have been used to prevent numerically unstable algorithms being buried into hardware. So anyway, hope that helps. The pieces, these are actively live. These are not, none of these are pure research projects. So we're based in Intel graphics. We are applied research. Nothing that you're seeing won't enter production.
Right. Okay. If I just ask my last question for now, could I use this to design my next FPGA design?
Oh, this is a great question. So here's a little bit of a story that I think is very amusing. So here's a great question. So this is one of the eGraph questions that came up. So a slightly simpler question is, this is all ASIC targeted. Mm-hmm. But let's say I had one of those fixed block DSP things that can do, I think, like 18-bit multiplication, whatever it is. Now, of course, you can wrap that 18-bit thing with modifiers. And so in theory, it can do lots of different functions. Now, the eGraph technology would allow you to basically, it could contain all possible functions with cheap modifications to the inputs of one of those DSP blocks, whatever it is. And it could tell you for a given application the best way of porting it to the DSP block. But also the converse is true, which is if you have a set of algorithms that you want to target, what you could do is very interesting. You could put all of them in the same eGraph. So you have all these different inputs, all these different outputs, and the eGraph will do maximal sharing. That's one of its key purposes. So then that eGraph could itself suggest components that you should build, and therefore suggest fixed function that you should put into your FPGAs. So that would actually help you design, some hard macros. So that's one way in which this could achieve hardware architecture.
Right. Well, thank you very much. And let's talk more later on. Well, any other questions? I don't want to ask all the questions. Paul?
We should wait to see if anybody else has any questions. But I definitely have questions. I have slightly vague questions, actually. I'm really intrigued and rather frustrated by the verification story. I'm not frustrated with you, I'm frustrated with the state of the universe. I think you and I have talked a little bit about, so classical numerical analysis, all that numerical analysis around things like how do you solve differential equations with the finite element method or something like this, it tells you a lot about how many degrees of freedom you need.
Mm.
It doesn't tell you very much about how many bits you need.
Mm. Yeah.
Yeah. And so, one of the things you might, what those people can do for you is they don't tell you how many bits you need, but they do tell you how, as you increase the resolution, you should expect the precision of the precision of your solution to increase. And if it doesn't, it's because there's a bug, basically. It doesn't tell you what the precision will be, but it tells you how quickly it should improve.
Yeah.
Which is unfortunately, really clever, but not quite what we need. Yeah, maybe I'm just making a speech. Let me put it to you more precisely. You've talked about empirically figuring out how a particular expression evaluation needs to be implemented with your arithmetic. The question in my mind is, can we change the question in order to get a better answer?
Yes, so you might like this piece of the puzzle. This is actually incredibly entertaining. A lovely use of these curves. Where is this? Okay, let's go back to this. Okay. So here's something magical, which I think is really cool. This is a Pareto frontier, and it contains precisions, but it need not. It could also contain a variable, a single bit, which chooses between two algorithms under a certain condition. So it could be a condition number, like if the input is bigger than k. So, and you make k a variable that is searched on. So you can use this Pareto frontier to find condition numbers. You could also use it to find the conditions under which you would have more than one iteration. Should I use n iterations? Then that number of iterations could be in this.
Yeah.
So that's how you can use this exploration. So one of the lovely things about this is that if there's somewhere in your data flow graph that needs more precision, this will find it. So you clearly have that area where it will automatically do what people have been doing by hand, like this variable in the middle of your algorithm is very numerically sensitive. You'll need more bits. This will automatically find it. But similarly, by changing what goes into this search, you can choose between algorithms, you can conditionally choose, you can ask a whole range of different questions that actually is architecture design.
Yeah. So one of the things you might do is you might have different expressions for evaluating the same thing, but the different expressions have different cancellation properties.
Yep.
In fact, they suffer cancellation losses under different
ways.
Value range conditions, which we could test for. Right?
Yep.
So simply, I mean, in software, this would work. This does work well. You can simply flip between different implementations depending upon the value ranges you encounter.
Yeah. So the way that would work in here is you would have to create the architecture that does say, we could, for example, take an input. This is clearly very normal for like transcendental function implementation. I take an input, I slice it into 3 pieces. I define the edges of those pieces based on some numbers. And those are 3 variables that go into this search. And the tool will find what those values should be so that you would choose the correct implementation if X happened to fall in a particular range.
Yes, yes. Yeah, I was also kind of intrigued by crazy ideas like transforming the problem on each iteration of the loop in order to explore different sensitive ranges, because hopefully some of the time you'll be fine and you'll correct it.
So yeah, I think the sad thing is that you would have to generate all those architectures and then feed it into this to ask that question. But in theory, the fact you can do an input domain split, and then you can do an intermediate variable domain split. Nothing stops you doing that, but you would have to include all that freedom in the design, in the search space, which is not a problem, but it's not going to. So one thing that you could do, which is actually very funny, is I didn't present automatic rewriting of the algorithm. So there are tools that do this. There's the University of Washington that we work with has a tool called Herbie, which will automatically rewrite the floating point algorithm to improve accuracy. This thing I'm showing here, we have been suggesting, ideally you want something that will rewrite the algorithm. You'll want it to do domain splits, and you'll want it to find precisions. And in theory, a lot of these techniques we've been describing today, like eGraph rewriting, combined with these kind of Pareto searches, can do that. So that's certainly on the roadmap as well.
Yeah, it was the Herbie work that I was kind of thinking of, absolutely. Yeah, thank you.
So we have people who are keen on that question. The other thing, of course, that I kind of component selection. So I haven't touched on this. Like in my beginning of my presentation, I said, I need these components. I didn't say how those were chosen. In normal, it's just like, what do I have lying around? What am I prepared to build? Whereas really component selection is actually buried in this exact point of these Pareto searches as well. So do I use an FMA or not? Do I really want to burn that cost? The problem, of course, is the x-axis is a dummy cost metric. So, of course, clearly it's flawed, but it's sum of precisions. So if I happen to decrease one precision bit somewhere and increase it somewhere else, that's not ISO PPA. But anyway, this is that classic question. We're trying to break the very long feedback loops of design. But yes, there's some interesting elements there.
Yes, indeed. Thanks. Yeah.
Okay, great. Are there any other questions? Well, if there is not, so thank you very much, Theo, again, for your lovely talk. And if we got some research ideas, we'll contact you and hope you do not mind. And,
so we definitely have, so the rover one is, so we're working with George Constantinides in EE. So this is active in Intel Imperial collaboration. So yes, I think there's lots of other interesting questions. I think the eGraph question around the algorithm side to the far left is incredibly interesting.
Yeah. Oh, do you have a paper describing all this?
Oh yes, we have one of the key rover papers. I think that I'll send you a pointer to that.
Yeah, that'd be great. Yeah, I think it would be very interesting to see how the 6 steps could sort of fit together in a research paper that we could refer to.
Oh yes. So I think I have a rover paper. This kind of landscape I'm describing, hopefully this year we will start, it'll probably be more industrial white paper type stuff, but at some point that this story will emerge.
Okay. Okay, great. Sorry, Paul, you
I have more questions, but I should release other people on the call.
Okay. All right, great. Well, thank you very much, everybody, for attending. If you wish to stay a little bit longer and if Theo is still available, then
I'm available for more questions. Love questions.
Okay, great. Yeah. So anybody want to disappear, feel free to do so. But if you are interested to hear more, then time for more. Paul.
Yeah, I was just curious. You talked about your multi-precision implementation strategy. One of the things you can do with a multi-precision library is actually figure out where the precision is being lost, where the cancellation is happening. You can actually catch it. You can see where those massive normalizations are taking place, for example. Can you use that information?
So those magical places when there's massive cancellation and you need more bits, so that would come out of that Pareto search frontier. So when it says, when you select something on the frontier, you'll see that everything might be 16-bit, but this thing down here is 20 or something. So what that then means is, we have to build larger components at that place, but we have parameterizable components flying around. So basically, what we're hoping, the Pareto search should be scrubbing areas where the precision is not useful. So every time the bit width shrinks, you're going to get PPA benefits. So that's really, you're basically polishing the precision landscape. That's the goal.
Yeah.
It's not formal.
I guess I was thinking that we can accelerate that search. You don't simply have to try lots of variants. You can just see where the problem is.
Oh, sorry, how would you see where the problem is? We're basically trying to prevent any human involvement of
Right.
numerical analysts.
Yeah, I mean, what I'm thinking about tools that we've played with and other people have played with, which are like program profilers, except they tell you where your position is being lost.
Mm-hmm. So then the interesting question is, so if precision is being lost, in the current approach, you just end up using more bits in a certain place that might end up being untenable because you need too many bits. Otherwise, it basically says this is not the correct algorithm. And so you would have to start rewriting the algorithm to avoid that.
Yes.
So I suppose in that Pareto search, either you could see it's numerically unstable. So there is a question there about whether this is a sound argument. But obviously, if you have an algorithm where adding hundreds more bits won't improve your accuracy versus an algorithm that's more numerically stable, then we are expecting that the more numerically stable one will result in smaller hardware for a given accuracy requirement. So there is a question like, when do you go back to the algorithm design? And then the question comes, there are these techniques now. It's one thing to know when the cancellation is happening. What do you then do? And so either is it an algorithm redesign that goes back to tools like Herbie. I mean, it's been called a drunk numerical analyst. But now here's the question, and you mentioned it earlier about the, should we be happy? I mean, the landscape I'm proposing, it is quite amazing that I should even be doing this because I don't have the tools I need to answer these basic questions. So it is very interesting about, yes, if somebody tells me with much wisdom, this place in your algorithm is numeric, is where your precision is going, you're losing all your accuracy, then I just say that's lovely, but what do you expect me to do instead?
Yeah, I mean, another attack on this, I'm not sure how feasible it is, I'm sure somebody's tried it, is the kind of concolic or symbolic execution, and then trying to use an SMT solver or something to solve for the inputs that cause your cancellations, for example.
Mm-hmm. Yeah, so that is the other piece of the puzzle, isn't it? Which is, so that's actually very interesting now. So earlier I said you can split the input domain, but that would be a conscious upfront choice. And it may not localize to the area of disaster. And the form of disaster may be very ugly. Like, what is the input domain? Or what's your multivariate input domain that causes you issue? And how would you get out of it? Mm-hmm. So then the concolic would give you, can it give you the input domain that is disastrous? And then you can special case those.
So Daniel, we're struggling to hear you.
It's crap. Assuming you can have a safety condition that describes a disaster, the answer is yes. So you need to be able to tell it what is a disaster, right?
Okay. I think I still have some audio issue. So you can say the input domain of a disaster. Is that right?
Yes, you can.
Yes. Okay. And so then the question is, what is the definition of disaster? And then if you know it's a disaster, how would you, it's actually a really cool question. So if you then restrict your algorithm to the disaster space, how should you change the algorithm so it's not a disaster? So there's the condition creation, which sounds like is doable. And then there's the what do I do instead? That's cool. Okay. So that is, so this is very interesting.
Are you working on this kind of thing, Daniel?
Symbolic execution stuff, yes, even with floating point numbers. The specific stuff, of course, never done it before.
Mm-hmm.
But that is interesting, isn't it? So if we go back to the overall, there's, as I mentioned, there's this whole, you have to give that Pareto search tool things to search. So you have decided the architectures of interest. You've decided the case splitting of interest. All of that is predetermined. But if you were to turn it around and say, I love what you're doing with your algorithm, but there's this disaster, which hopefully the test for disaster is cheap, or there's a question of how expensive is that test. And it could also be, the other thing that we've seen before, of course, is the input test might be horrific, but it might just be a local test. You know, you're about to enter this tiny set of operations. Could you just transform this? I mean, you know, the famous, if you look at the Herbie thing, like the classic example is the difference of square roots can just be rewritten as 1 over the addition of square roots, that kind of stuff. So you could make it local.
So I was actually thinking about a similar question in a way. Given that you now have a Pareto frontier that says, okay, we're maybe off by, we're almost at the precision that we want, but not quite. I know that for a bunch of these numerical algorithms, a posteriori fix-up is the method of choice, right? So you almost get there, and then you have a look if you can almost fix it up. Is that anything you've been looking at? Because I mean, in the end, it goes into a similar question, right? So if you can figure out that you're always half a bit too small or something like that, is a fix-up possible that makes a better compound algorithm than the algorithm that was originally coded?
I mean, the weird one is like, you know, so the original discussion is around, here's 3 algorithms. Can I do a domain split to choose between 3 of them? But then, yes, the more interesting one is either an iterative algorithm or a fix-up algorithm, but you still, for the tool to kind of search the space, you need to know what the algorithm is. But in theory, I mean, the classic, like, how many iterations do I need? Unfortunately, these at this moment is just simulation based. So it will show you that you may need more iterations, and you could get some stats out of the simulation to see when you would need more, but it's not going to give you a concrete architecture, because you may need another one and you can't find it. You might need another iteration, but you haven't, obviously your simulation won't catch the moment when you need that. So there is the formal proof element side of things. So that has 2 forms. So one of them, certainly it sounds like through symbolic execution, if you have a concrete executable definition of accurate, then you can shrink down a domain of which you're concerned. But even there's interesting, isn't it? Because we said we may not want it as a function of the inputs, we may want it as a function of the intermediate variables. But the other side then is the lack of, do we actually have an application level proof of correctness that could then be wrapped around this search?
Yeah. So basically, for symbolic execution to help you, you need to be able to somehow express like this can go in either direction, right? You can just have a algorithm that you know is good enough and compare whether it gives you the same results. Or what is sometimes more interesting, especially for like square root or similar algorithms, is to just go the other way, right? I have a result, I square that, I want to get within a certain distance of my input.
Yeah, so we have situations where there is, do we have an quick application level, yes or no? I think what's fun in the ellipse example, which is very entertaining, in theory, well, you would need access to the infinitely precise result. That's one of the interesting gotchas here, which is because what's really very interesting, particularly with floating point fun of multi-precision, you know, any precision change has a bit accurate consequence. And do you really want to be close to the previous, say, uni-precision implementation? Is that your golden reference? One of the things we were trying to do, obviously, with the whole FP core stuff is we want to have you know, the mathematical reference. We don't want to be, we have seen it before, but it can get incredibly irritating. Imagine if you're being held to account to a floating point implementation that exists, and then you're trying to reason about how far away you are from that floating point implementation. And what happens when you realize that your answer is better, but the original answer is shocking, but that's your golden reference. So you end up with these horrific arguments. And normally your implementation then crashes and burns because theirs is uni-precision and yours looks crazy. So there is certainly that question of, do we have an executable yes or no to application correctness? And I mean, does it run a reasonable time?
You could also go ahead, like, you know, like the question of symbolic execution is always, how bad do you want to kick the SMT solver, right? The poor thing's already getting abused all the time. But they do have, there is like rational and real solvers in there. So potentially you could be able to phrase your actually, you could say like, I want to compute the square root of 2, period, right? And see how close you can get to that. That of course makes it even harder on the SMT solver, right? Like theoretically.
So I think the fun, clearly what this points to is my kind of multi-precision simulator step. In truth, it should be decomposed because I've discussed it as smoke tests, because you can basically say when it's complete nonsense, go back to the drawing board in whatever that form that is. But once you start getting closer to the answer, which could be this input domain is dubious, go look. Once you get to that turf, you know, you really are heading down. I need to know if the application is correct. So I think there's something very interesting here, that particular space between simulation reasoning, simulation with some SMT, and then you really do need, you know, an application level formal proof. So I think my step 2 should decompose into potentially simulation first and formal refinement second. But that's really interesting because, you know, what we're describing here is algorithm design and architecture design. And at this stage, there's no PPA cost, you know, that we're actually describing. So that's the other interesting piece of this. But yeah, that's interesting. But yes, definitely that step 2 is clearly not bulletproof. And there are a range of interesting hybrid techniques because yes, the simulation approach with particular SMT queries can help you. You're basically wanting to apply more formal methods once your smoke tests are clean in general. So that's quite interesting. And how it relates to algorithm design. That's the bit that's particularly fascinating. Not just analysis, because one of the really cool topics in general is how does formal verification do design and improve performance, not just prove correctness. That's actually a very interesting space.